What do you say? Probably. Yeah. You want to skip it or?
Well, there's another seminar around this time.
Yeah, I mean, you're here. You should just. You're here. You should just attend. I guess.
Sorry.
Yeah.
Almost late. You're gonna find it.
Is it offline or?
It's like if we are calculating a smeared version.
Are you just connected to Zoom?
Yes,
Perfect.
the explanation. For the difference between a smeared version and unsmeared version, I didn't calculate what's the W minus W smeared. This is difficult to calculate. Rather, I will quantify it using the momentum resolution or the energy resolution, because in real life you don't have to and the momentum resolution, that part is polynomial due to the transfer. Yeah, but the calculation of smeared transfer itself is
Can you make it start the presentation?
But when you smear it, it's changed.
I don't think you will change the results.
Is this the relevant mic or?
So if the momentum is
Yeah, there's mics in the room.
Everyone. So should we mute this one? Like
No,
the
this-
laptop
this-
mic, I mean?
So instead of looking at just one dynamic momentum piece, you're looking at some wave package.
Can you hear us on Zoom?
kind of, so yeah, so you see the process and people call this
Yes,
we
loud
can.
and clear.
Okay.
be avoidable.
Let's just not hide.
And
Exponential is good.
yeah. So yeah, so
Hide.
so as long as
It's being recorded.
of our
Sure.
it's finer than the net with then the in Euclidean, for single hydrogen, for every time you feed there's a mass gap. So if you smear it, because it's like the delta function here, which is
You're a postdoc.
you smear it,
You're a postdoc.
the overlap between these other parts or the overlap between the smear result of their values is still very expensive.
Okay, well, let's get started. We're very happy to have Torsten Zache from Innsbruck. He's been postdoc there since 2020. He's been doing a lot of really nice work in the theory of quantum simulation for lattice gauge theories, among other topics. We presented some of this work at QSIM 2 years ago. That's where I first got to know Torsten. And he's accompanying Peter during his visit to Maryland this week, so he's around all week. We're going to chat with him more. And today he's going to tell us about not just theory, but also experiments probing high energy physics simulation.
Okay, thanks for the introduction and thanks for having me. Exactly, so I will be sort of giving a half experimental talk, I guess, presenting results that we have obtained well together with QuEra. So before I get there, let me tell you why we care about doing what we did. And the overarching goal is really to use quantum simulators, either analog, but eventually also digital quantum computers, to simulate gauge theories. And there's, of course, different motivations for doing so. And the one that I prefer comes from high energy physics, from particle physics, where you may want to simulate, parts of interactions as we believe they appear in nature due to fundamental particles, for instance, how quarks interact through the exchange of gluons as described by QCD. So we have this theory. In principle, we know how to write it down, but unfortunately, it's difficult to calculate certain things. For instance, this is a phase diagram of QCD as a function of temperature. There is a crossover from a sort of confined phase of hadrons that make up everyday life to a deconfined phase where there's a soup of quarks and gluons, really. And it's not entirely clear how this phase diagram looks like. And the difficult part is actually going to finite density. So what plays an important role here is the density of fermions, so fermionic matter, the sort of, how many protons you have, let's say. So this is what's difficult to calculate theoretically. So experimentally, of course, this has been probed for ages. And one of them, some of the most sophisticated experiments probably that exist on the world are sort of these large colliders where you smash different types of hadrons, for example, together. And what's quite interesting about this theory and also about the physics of it is that it displays this feature of asymptotic freedom. It shows you that if you go to higher and higher energies, you can actually describe it relatively easily in terms of perturbation theory. Things become weakly interacting, but sort of the counterpart of this is that the physics gets very non-perturbative if you want to describe the low energy properties at large distances. So this is sort of the counterpart of asymptotic freedom, is this confinement that is hard to deal with. And that underlies sort of what's going on in these experiments. So when you want to simulate such an experiment as a theorist, there are of course different tools on the market, but sort of really the gold standard are lattice Monte Carlo simulations. So you discretize these field theories that I'll talk a little bit about more in a moment. You put them on a spatial or space-time lattice, and then you put them on large computers, and you basically do Monte Carlo sampling. And this is extremely successful whenever it works. However, it doesn't always work, especially when you have what is called a computational sign problem. So roughly speaking, these are Monte Carlo methods. So you get sort of things that need to average out. And if you get large positive and negative signs and your signal is sort of hidden in the sum of of many positive and negative numbers, then the statistics get very difficult. And that's roughly speaking the issue. So this happens generically for quantum many-body systems whenever you look at real-time evolution, simply because you need to average sort of phases that can be complex. And it also happens in other physicals. So for instance, if you wanted to simulate a heavy ion collision from first principles in real time, that's not possible really without further approximations. The other situation that is sort of common is when you have finite number of fermions or fermions that are sort of imbalanced, similar to the Hubbard model, where you're maybe familiar with when you go away from half filling, you get a fermionic sign problem. The same is going on in QCD. This is sort of the axis of fermion chemical potential going away from half filling, if you wish. And that's why you also encounter a fermion sign problem in this simulation. And this is, of course, where quantum simulation comes in. We want to overcome this eventually. If you don't like the high energy perspective, H theories also play an important role in other fields of physics, for instance, topological order and condensed matter physics, and then also here, I guess you're very familiar with the theory of quantum error correction, and so there's many parallels to topological order. I will not really be talking about that at all, disclaimer, but I'd be happy to chat. I'm very interested in this aspect as well. Okay, so this is my personal motivation, I think. Before I jump into what we've been doing, let me tell you a little bit more about sort of why this is difficult on a technical level. So when we want to do a quantum simulation, we usually write down, instead of action-based formulations for Monte Carlo simulations, we write down Hamiltonians, and the generic Hamiltonian of the lattice gauge theory looks something like that. So it's a lattice model, and you have typically two different types of degrees of freedoms. So for instance, let's look at a 2D spatial square lattice, and then there are degrees of freedom that represent the matter that live on the sides, and there's H-field degrees of freedom that live on the length. And the reason we do that is because we want to implement these gauge symmetries. So that's the defining feature of the lattice gauge theory, is that you have this extensive number of local symmetries or constraints. So you prescribe some gauge group, let's say, and then there are operators, Gauss law, so-called Gauss law operators, that live on every side of this vertex that tie together the sort of electric fields, let's call them, so the gauge fields, at the surrounding links to the matter contents, to the charges that are associated with the matter that lives on the sides. So whenever I have a model that sort of respects these kind of symmetries, I call it the lattice gauge theory. So in a wide sense. So then you can write down Hamiltonians that commute with these operators, and they generically take a structure like this that sort of comes from decades ago from Torsten Zache. So you have electric field terms that somehow penalize different gauge field configurations, but then the dynamics of gauge fields is inevitably higher dimensional. So you need for gauge fields to propagate, similar like the photon in this beamer is propagating through space. It actually needs a magnetic field to oscillate. So electric fields are not enough. You need some sort of an extra term that gives dynamics to the gauge fields. And the smallest one or the simplest one you can write down is something like a blockade operator. So I'm not telling you exactly how this looks like in detail, but in practice, it's always some sort of a four-body operator that tells how you can displace a flux string, for instance, by letting it fluctuate transversely. And that's why the real gauge theory physics is only happening sort of in 2D and 3D in some sense. And then if you're interested in standard model physics, there's also a technicality about the involved degrees of freedoms. So the degrees of freedom, the gauge field degrees of freedom that live on the links, they're described by some sort of group, some sort of symmetry group. And the Hilbert spaces have a size that corresponds to the size of that group, basically. So if you're interested in groups like U1 or SU2 and SU3, these aren't necessarily infinite dimensional in the typical way. So you need to truncate that somehow if you want to represent it on a quantum computer. That's actually a severe problem, also on a quantum simulator. So it's something you have to think about. And then finally, the reason we have gauge fields sort of in nature is to describe how matter actually interacts with each other. So the purpose of these gauge fields is not just to propagate by themselves, but to induce interactions among let's say, fermionic matter degrees of freedom. So this happens through an operator that again respects this symmetry, that needs to commute with this type of Gauss law, which tells you that whenever a fermion hops from one side to the next, let's say, it needs to drag it behind sort of a string of electric flux to be compatible with that symmetry. And then maybe you also have an additional sort of local mass term. So what this tells you is that these models are sort of generically of this shape. And it's also, while it's not clear how to best represent the gauge fields, it's also not entirely clear how to best represent the fermionic matter fields, because neither of them are really qubits. And then ultimately, if you're interested in doing high-energy physics, this is just a lattice regularization of a quantum field theory. So while we're kind of far away from that, eventually it might be necessary, or it will be necessary for this application, to take some sort of a continuum limit to sort of make this lattice finer and finer, adjust the couplings in an appropriate way to actually get to a limit where this describes, let's say, the real world. Okay, so the theorist's dream would be to come up with an algorithm that simulates these class of models. Remarkably, this has become an experimental field over the last decade or so. And I want to sort of highlight that our hope here was to use the tools that are available right now and do some of the physics that is sort of genuine to gauge theories. So in that sense, what we want to really focus on is constructing models that are bona fide in gauge theories. So they have these local symmetries, but they also have some aspects of sort of the real thing, like QCD. So we need to go to physics that is in higher dimensions, where 2D is the simplest example. So experimentally, this has become an experimental field about a decade ago or so from a famous experiment from Innsbruck. It was more of a proof of principle example that digital quantum computers at the time have become sufficiently sophisticated that you can actually run trotterite real-time algorithms for a simple version of this gauge theory. This was actually a sort of a 1+1 dimensional version of quantum electrodynamics on a sort of minimal example, which is quite impressive for the time. And then many other people and platforms jumped on this program and tried to compete. And I would just want to highlight quickly sort of the diversity that exists in this field. So this was a digital trapped ion simulation of a 1+1 dimensional model. Now in 2D, the first one that happened, I think, was this one. So in 2020, people started using IBM devices on the cloud and simulating, for instance, sort of two plaquettes, so in some sense minimal 2D. This was a non-abelian gauge theory, heavily truncated digitally with superconducting qubits. Also in Harvard, people were studying analog systems. They were not actually after gauge theories, but more about this deconfinement in topological order. But this experiments with Rydberg atoms, analog simulations with Rydberg atoms, actually can be interpreted as a specific type of C2 lattice gauge theory, very much related to what I've been talking about in a minute. Also in Innsbruck, people were playing with variational circuits to do, for instance, the one plaquette models of your one gauge theories with trapped ions once again. With trapped ions, but digitally, this is a continuum work, people were realizing topological orders. So this is also interesting sort of for state preparation purposes. Similar things have been done also on superconducting devices. This is from a group of in China, so-called stringnet models that I personally find quite interesting, actually. Also here, people were using trapped ions, for instance, to run sort of minimal sort of rings of plaquettes in a Z2 lattice gauge theory. There was another work from people in Japan just recently. So you see sort of this whole thing picked up in like the last year, basically. There was an explosion of works where people again focused on quasi-1D systems that had plaquette interactions. There was a work from Google very prominently last year. Again, I'm focusing here on the 2D cases where they basically use their superconducting devices to run variational state preparation and then a little bit of real-time evolution on top. There was another one by Continuum, it's also focusing on minimal 2D instance. So as you can see, sort of many people trying to do different variants of the same, just figuring out what is achievable. So what I will be talking about today is a line of works, not just ours, but sort of many that appeared more or less in parallel, that ask the question, can we do physics with these platforms? Yes, please.
Are you going to talk about, it's not your focus, but the quantum advantage question?
No.
So you don't think there's a path to quantum advantage in this, or?
No, I think, but I will not use the word in this talk.
I mean, none of those, were any of those experiments even close, like even the Harvard one?
I'm not sure, honestly.
And the one you'll present, is it on the path, or?
I mean, as you can see from my reaction, I'm very hesitant to make any claims. I think they're.
Well, no, can you simulate it classically?
I think all of those that I have talked about and that I will be talking about have been simulated classically. And then it's a question of, like, is this exactly reproducing the experiment, or is the experiment doing something that is not captured in the simulation? And is that deviation, what does it mean? But I think I personally believe that it is possible, if you scale them up a little bit more, that we cross the border of what is classically simulable. So I think we're sort of on the path, but I don't think we're there like today. That's my opinion, but maybe. No. Okay, so what I will be talking about instead is trying to see, can we do some physics with them? Okay, and that doesn't necessarily mean that we, in a quantum advantage regime, it's more like, can we see the physics that we're eventually interested in seeing in something like QCD? So there's a number of works that I'm putting here on the side that did this last year, more or less at the same time. And one of the or maybe the most sort of obvious physics application is this question of confinement. So let me, in a pictorial picture, just explain it in 2 sentences. As I said earlier, gauge symmetries force a connection between charged matter and gauge fields. So that's sort of the definition. So there's always some sort of a local conservation law that tells you if there's a charge, for instance, like a positive charge, and there's a negative, then field lines, electric field lines emanating from that charge have to end at some negative charge. So there's always this sort of connection between the gauge fields and the dynamical matter themselves. And if you have a theory that is confining, then that again is basically defined by the following feature, is that if you take 2 charges, you place them at a certain distance, and you ask what is the energy of that configuration with respect to some vacuum. And then you will find, I mean, it's sort of a definition in some sense, if you find that the energy grows linearly with the distance, so you can think of a classical force, which is the derivative with respect to the distance, then it's not possible to separate them really. All right, because no matter how far you pull them apart, there's always a force putting them back. So they're confined in that sense. And technically, there is a parameter, the string tension, which tells you how strong that force is. It grows linearly, so the energy grows linearly with the distance. Now, if you have a theory that is confining, so like QCD, and it also couples to dynamical matter, and then what can happen is that at some point, the energy that is stored in the flux string becomes so large that you cross the threshold for sort of particle-antiparticle pair production. So if you have some particles of mass m that are sort of accessible within that theory, if you pull them apart at some point, there's enough energy here that this will sort of break, this string will break, and instead two new particles pop out of the vacuum, so to say. And very roughly, this is sort of what's underlying this idea of confinement and string breaking. And this very much was a number of people, including the one you work that came out of here, and also what I'll be talking about. For example, this well, many more like this Google work I was mentioning earlier. People have tried to sort of see how much of this physics is actually accessible on real devices. Okay, so let me now finally get to what we were doing. So this is a work where we used an analog simulator. It's very much a sort of traditional experiment in the sense we were not accessing any device through the cloud. We're actually talking to the people at QuEra who run this their machine as in analog mode, sort of as a traditional Rydberg tweezer experiment in some sense, though with this additional programmability that their device offers, and that was kind of very important for this to work. So on the QuEra Harvard side, there was a number of people involved in this. So Alexei Belinsky, for instance, was sort of leading the experimental part, and Maj was sort of running this. And then from the Innsbruck side, let me emphasize, of course, Peter, who's here as well, and Daniel, who was the main driving force sort of to actually push this through to completion. Daniel used to be a postdoc together with me in Innsbruck, has sort of had a short stay in Harvard recently, now is getting a permanent job in Spain. And here's the reference if you want to have a closer look. Okay, so let me briefly talk about Rydberg atom arrays, though I'm sure many of you know the background. So the idea is, or the underlying hardware capabilities are basically that you have individual control over neutral atoms. So you can isolate them, you can trap them individually in so-called tweezer arrays. So you trap them in optical traps that you can individually control. So you basically have the freedom to put the atoms wherever you want, sort of. So at some locations L. And then you can treat each of these individual atoms that are fixed in place as small quasi-spin 1/2 systems. Okay, so they can either be excited or in the ground state. And then the generic Hamiltonian that in an analog fashion describes these experiments very well, if you also drive them by laser light, looks like this. So there's an operator that drives the transition X, so it flips the spin from the ground state to the excited state and back, and it does so with a characteristic gravity frequency omega, and it does so on every side. And this is by by laser excitation, so it can also be detuned, so it can be a little bit off resonant if you want. So then it's favoring either doing it like it's favoring either the ground state or the excited state. So this operator here counts the number of excitations in the excited state, 0 otherwise. Sorry. Okay. And then maybe the most important part about these systems is that they are very strongly interacting. And the reason is that you excite these atoms not to an arbitrary state, but to sort of to a high-lying excited state, a so-called Rydberg state, where there's a strong van der Waals interaction between two atoms when both of them are simultaneously excited. So it's van der Waals, it goes like the distance to the 6th power, and there's a characteristic scaled sort of number to that. So each of them are sort of pairwise interacting, and if they're close, this interaction is very strong. If the further apart, then you can basically neglect it to a certain degree. So to capture this strong interaction, people introduced a so-called Rydberg blockade radius. So this is this idea that really, if you're sort of within a characteristic distance, and that distance is defined to be, well, that distance where the interaction's energy is as large as the driving strength, then within that distance, you can basically not excite two simultaneously. And outside of that radius, they can be simultaneously excited. So if you want, this is a local constraint that tells you that within a certain region, things cannot be simultaneously excited. And that's sort of the basic idea how this connects to gauge theories on a high level, is that because of this strong interaction and by sort of choosing specific geometries, you can implement local constraints. Yes?
Can I just ask a question about the choices here? So when people do quantum computing, they usually use different hyperfine states as the encoding. Well, would you have an option in this analog setting? Like, would it have some disadvantage or
So I think the way I'm saying it is the Hamiltonian is sort of always on, and you could
I see.
this Hamiltonian is true when you have ground state and Rydberg state as your sort of logical information, if you wish. But you could imagine a sort of a little bit more sophisticated setup where you sort of at some point store the story in some hyperfine state where this Hamiltonian is not acting. So you could sort of turn on this whole analog processor
But
and
you
then
wouldn't
turn it off.
really call that analog anymore.
Oh, it's sort of it's a hybrid. I don't know. It's so for me, I would put that in the box of a programmable analog setup, which is of course becoming a digital device eventually. But we didn't explore that here. But I will come back to that in the end because,
Okay, thanks.
as you will see, there's sort of more that we would like to add to the Hamiltonian. Okay, so if you do that, then it turns out that, or we asked ourselves, is there any configuration where it's particularly sort of appealing from a gauge theory perspective? And we're going to guide you through the idea briefly. So we choose now the geometry to be that of a honeycomb lattice. So more precisely, sort of the links of a honeycomb, so cargomane. So every dot here is the location of an atom. Okay, and the atoms can be either in the ground state, which are the white dots, or they can be excited in the Rydberg states. And here again, sort of the scheme for the parameters. And now the idea is that you choose the flexibility of the device to dial in a specific geometry where the Rydberg blockade radius is exactly chosen to be sort of this red ring. Because what this tells you then is that nearest neighbors can never be simultaneously excited. Okay, if you take the blockade sort of as a hard constraint. And this allows you then to sort of to think about what are the possible configurations that are locally allowed. Okay, so there's a specific sort of reference that I'll come back to in a second. So, but then if this constraint of having at most one excitation per vertex translates into precisely 4 states, right? So you can either have exactly 1 excitation or no excitation. And depending on whether you're on A or B sublattice, sort of these 4 look a little bit different. So then there's one setup in the experiment where there is a natural ground state of the system, which is this ordered pattern that you see in the background, where you have this sort of 1/3 filling, and it's like, every red sort of point to the south left, let's say. So you have this staggered pattern. And if we identify this configuration as the vacuum, there's a nice interpretation in terms of gauge theory dynamics, just by sort of mapping this 1-to-1 every configuration that is in this blockade space. So we call this sort of a bare strong coupling vacuum, if you wish, like it's empty. So there is nothing in there, if it's in this specific configuration. And then the others you can interpret as sort of charge and string configurations. So pictorially it looks like this, that these 2 configurations mean there is a string sort of passing through this way. And when you have a deviation of this sort of 1 excitation per vertex, then you can associate a dynamical charge that is sitting on that location. And then there is a precise way of mathematically identifying sort of the occupation of the Rydberg atoms with a spin 1/2 degree of freedom. And there's a little bit of sort of bookkeeping of the signs in here, such that you can identify this spin 1/2 field as an electric field, which is either there or not there. And then there is a Gauss law in the background that specifically selects those 8 configurations, so 4 per vertex, as those that are identifiable with the divergence of that electric field, which is if there or not there, equals the charge that sits in here. Okay, so if that was a little bit too quick, I invite you to have a closer look at the discussion in the paper, but pictorially, I think it's very clear. But you have just this local constraint, and that tells you whether you're either in this reference configuration or you have some excitations on top of that reference, and we can now interpret them as either dynamical charges or as strings passing through the system. And in a technical sense, this is a so-called U1 quantum link model. Yes?
Why do you call that a Kagerman? Where's the Kagerman enter? Sorry.
So it is a honeycomb, but the vertices, sorry, the links of the honeycomb, they form a Kagerman lattice, right?
That's what you mean.
Yeah, so it's just links of the honeycomb, and that's for me the natural way to think about it. It's just this geometry. Yeah. Okay, so what you can also do in these experiments is you can just leave out some atoms. So literally don't place tweezers. So for instance, if there is no tweezer here, or actually these 3 tweezers are not existing, then you can always interpret this as there is no Rydberg excitation, because there can't be, because there's not an atom. Again, it turns out that in this mapping, this precisely means that you place a static charge. So you sort of force this configuration, which is empty. So in that sense, you can create point defects in this sort of condensed matter-like system. And because of the symmetries of the system, the ground state will naturally pick a line defect that connects these 2 point defects. And that is the picture you see sort of on the left. Like it's a geometry where there's two times three holes. And then the sort of the ground state of the system will dynamically look like that. So let me show you how that actually happens. So now from theory, we can sort of interpret the Hamiltonian and just rewriting it in a technical way differently. So it's the same Hamiltonian as before, it's the Rydberg Hamiltonian, but now we interpret this just driving term in the middle as a dynamical excitation hops from one side to the next and changes the flux in between. This detuning term that we had before, you can interpret as a mass term that just counts how many dynamical excitations are there. And what's quite interesting is that the long-range tails actually also are an important feature in this setup. So what I've said before about this mapping assumes a perfect nearest neighbor blockade, but in these systems, the long-range tails are not completely negligible, and they actually play an important role here because these higher order terms, they sort of sorry, it's still visible here. They sort of induce interactions at larger distances. And you can interpret this actually as an electric energy cost that strings can have. So to show you how exactly this happens, here are some DMRG simulations that calculate the ground state of this model, sort of the full Rydberg model on a geometry of that size. And what is plotted here is the electric flux, again, with respect to this background configuration. So white is no electric field, blue means there is electric flux present. And then we also show you the charge values. And these two simulations, they differ in terms of static charges that are placed at different distances. So these are the big blobs here. But there's also dynamical charges, if you look close, that are dynamically generated. And yes?
These first two terms, is this another way of writing the PXP model?
Yes. PXP on that lattice, exactly. It's PXP on that lattice plus the tails.
Haven't people studied PXP and indeed?
Yes. So people have, I hope there's a reference, what I will be talking about, have studied that, but sort of.
Oh, they didn't see the physics you were looking.
They didn't look at these static defects. So there's a work by Ryan and Sugir Sachdev and so on, who studied sort of the same phase that we're interested in.
Interesting. Yeah,
But they were looking for something else. Yes. So there should be a reference somewhere. Okay, so what you find is that as a function of distance of these static charges, you find different flux strings. Either it's this confined string, or you see that it can potentially dynamically break into charges that sort of screen the static defects. So you can make this more quantitative. You can actually look at the potential energy, sort of this energy of this configuration with respect to the ground state, meaning the one without static charges. And you do this as a function of distance. You see that first this potential actually grows linearly. So this defines the string tension, a linear slope here. And then it levels off at some point, which means that this broke apart into two configurations where it doesn't really matter which distance they are anymore. And we checked that indeed this sort of bare mass term here, the delta, that controls the point where it breaks, which tells you it really plays the role of the sort of the mass of those particles. You can also check what's the slope here, so you can fit a slope. You see that it's roughly independent of this mass, and the leading term, so the leading behavior of this slope is governed by changing the blockade radius, which means sort of playing with this energy term. And the interpretation is really that it's the next nearest neighbor interactions that see that there is a line defect that differs from the background pattern. So there's, this string feels that it's sort of wrong compared to its neighbors. So that contributes an energy everywhere. And that's why this energy grows linearly. And that's how you can rationalize also this functional form. Yes.
So I didn't know. So Michael's question was basically, is PXP related to the gauge theory? I didn't know that it was.
It is, depending on the geometry. So in 1D, it's kind of clear-ish. So there were some of the reference I thought earlier that people realized that in 1D, sort of there was this first PXP works, and then later people interpreted it as a gauge theory, and sort of repeating that story in a sense in 2D. where the specific lattice plays a more important role. So it differs what kind of gauge theory it is, and we have sort of specifically chosen this one because we believe it's sort of the simplest one given what you can do with the hardware. Okay. So it's PXP plus long range on a specific lattice, basically.
But the scars won't play a role.
Yeah, that's a good question. We had some discussions about whether what we see, what you'll see in a minute, is related to scars, and our conclusion was that at that point not, but in another parameter regime it may be. That's all.
It seems very different.
So it looks like you define like these like positive or negative charges, like these gray or red charges, depending on like the direction the string's coming out. Or is there more? Is it?
No, there's sort of there's a subtlety that I glossed over, is that this reference configuration that breaks a lattice symmetry, right? So there is a threefold symmetry breaking as our reference, and with respect to that, there is a unique labeling of whether you're an A or B sublattice, and that sort of gives a directionality. So if you indeed like I glossed over this because there's one string actually missing. So in this precise model, it's not possible. So strings can only go sort of east and north, which is a little bit awkward, but it is what's happening in this particular model. And then there's a convention whether that you call plus or minus, but they're opposite. Okay. But there is this directionality, and it's because there's a spontaneous symmetry breaking in the background. So in fact, if you now go do theory simulations, and maybe here I should have had another reference. This is also what Ryan and so on were doing. They realized that there is a phase in this model. When you tune sort of what I now call the mass versus the string tension, there is one phase, which is sort of a crystalline phase. That is the one where this lattice gauge theory interpretation makes sense. So this is the phase we're interested in. Yeah, sorry.
So these simulations, these are done for the map.
Yes.
And so if you put it on a torus with both directions, then we have features.
Yeah.
Is it going to change the physics of this strength?
So the way I think about it is that all of this physics is happening in each and every of those spontaneously symmetry broken sectors, and what we're doing is sort of valid at low energies, sort of above that spontaneous symmetry breaking. And we specifically choose that geometry. I mean, you see, for instance, that there are always these small tails pointing out. That sort of enhances the way the symmetry is sort of explicitly broken. So that's how we select one, sort of on purpose.
Different this setting, like these different sectors do not have each other. So.
Yes, so they don't here. So we're sort of deeply in one, and then there's excitations on top of that. Yes. So if you go now to 2D, this is the phase diagram that is expected. But now, so this was known. But what people have not studied is what happens to these point defects, which we now interpret in this lattice gauge theory language as static charges. And what you see is that in 2D, of course, there's different ways these strings can be connected, right? They could be, they could connect like this or like that. And then that's for this specific geometry, there's sort of 6 different strings that could by symmetry, they're allowed, that could connect these different things. And there's also, for example, this one configuration where it's completely broken. So then from theory simulations, we expect that depending on where you place them, where you put yourself in this phase diagram, so for instance, if the string tension is stronger, then you would expect the string to break earlier. Whereas also when you change the mass, this changes the distance at which it breaks. So if you pick a specific geometry, you could also vary the mass or the string tension, and then you would see that there is a region in the phase diagram where these 2 static charges would prefer to be, be screened by dynamical charges, or there would be other configurations where you find some sort of a superposition of those things, which is a sort of intact string. And that's the physics we're trying to see in the experiment. Our experimental friends, they ran sort of a standard adiabatic sweep protocol. So you initialize at sort of back here, you initialize your product state, and you sweep into this phase at different string tensions. And that's how we prepare sort of many points in here. And this is what we find experimentally. So this is again the same plot, and what I plot here is the sort of is a probability for finding specific configurations. So what we do in practice is, or what they do is they take a picture of the thing, they get a picture of the many-body wave function, and then you can identify which kind of bit string configuration you have. And you do it many times, and you count what kind of configurations you find. And then we sort of select a small region, or well, almost all of it, but sort of the region that is sort of between those 2 strings, and ask is it any of these configurations that I'm listing down here? And this is what you see experimentally. So the bars here are theory simulations, and the the other sort of non-symmetric ones are the actual experimental data. You do this experiment a couple hundred times or so, and you count, and with some probability you find some of these configurations. And if you sort of sum them up, you see that the whole thing is of course stressed and it's imperfect, so you don't get, it's not 100% a string, but it's sort of dominantly these string configurations in some superposition. And you sort of see roughly that this shapes follows what we expect from theory. And for instance, it's very clear that in this sort of specific location, for instance, it's not a broken string, but it's really dominantly a string. And then we do this in another regime, well, we do it everywhere, but we sort of analyze it in all the other regimes. Then you find that, for instance, up here, which sort of corresponds to the broken string regime that we expect in theory, you indeed find basically no strings compared to the large or large-ish, 8% level contribution of a specific product state, which you interpret as a broken string. Yes, please.
What method did you use to create the theory phase diagram?
These are GMRG simulations. So it's not simulating the sweep protocol, actually. It's just taking the Hamiltonian with sort of the best guess of the parameters and then just looking at the ground states. Yeah. So, I mean, given that that includes almost no experimental perfection, I think that agreement is actually pretty good. So we could probably do even better by sort of simulating a little bit more. Yeah. Yes.
Is there a reason it works well in QE? For GMRG?
Yeah, so I think, this is a gapped phase, and the correlation length is actually not very large. So the bond dimension doesn't need to be large. So in that sense, there's not a crazy amount of fluctuations in there. So that's why the simulation is relatively cheap. So this will be different if you go sort of closer to the phase boundary, of course. So when string tensions get smaller, this thing may fluctuate more. So you also see here that there's just a few product states that contribute to sort of a large amount of the wave function. So in that sense, it's not terribly strongly correlated, and that maybe explains part of my comments on why I think it needs to be way larger or sort of in a different regime to be in a quantum advantage regime, let's say.
But can you explain why the 1 and 6 are preferred?
Yeah. So roughly speaking, so if you translate that back into Rydberg atoms, these are sort of configurations where you just look at them where sort of they're on average further apart. So what happens is because of these static defects, the localized defects, the Rydberg pattern sort of wants to rearrange, and you sort of want to minimize, well, the energy basically. It's almost a classical argument. So if you look at just the classical energy that comes from the tails, then these configurations just have lower energy.
It has to do with the tails.
Exactly, it has to do with the tails, yes. So exactly. So the tails introduce sort of a geometry to the strings. It does not only depend on the length, as you would expect sort of in other models, but it really depends on the shape, and in some sense you want to be far apart. And that's why these extreme cases are.
But you might expect noise kind of washes some of that out. Is that maybe why the theory is so much higher?
Sorry, what do you mean?
Or no, the experiment is higher. Sorry. Is it which is which?
So the symmetric one, the bars, this is the theory. It's perfectly
yes.
Like
The theory is wants these configurations much more than the experiment.
So you might say that maybe it's finite temperature, or it's maybe you did the sweep, so there's actually maybe more coherent superpositions in the actual experiment than in the sort of perfect ground state. So all these, I think, is compatible with what you're saying. So this effect is sort of washed out by any fluctuations, either true quantum fluctuations or even just noise in the experiment or something like that. But we didn't analyze that in further detail, but I think that's what's happening. Yes. So I need to speed up a little bit. So there's you can also make this in real space. You can look at how this looks like. So this is this is how the string would look like. It's a little bit hard to see, but you can imagine sort of a little bit of a rough thing here in between. Whereas if you look at the broken string, again, if you look at the numbers, it's not purely a broken string, but you see this sort of the strands that are sort of loosening a little bit, and there's a little bit of color in between that corresponds to the dynamical charges, which in the actual experiment sort of try to screen this. So this is sort of the real space picture, if you want to see it. Okay, so then we wanted to do dynamics of this. So the idea is now we've understood roughly how to prepare those strings, and the question is now, can we see them breaking in real time? Which is, of course, eventually where this becomes really challenging also theoretically. So what we do is a lattice state preparation, and then we do a locally tuning quench. So there is the possibility in this setup to also introduce sort of a local mass term that favors the string configuration locally. So we can dial in whenever this is the ground state. So these are a little bit smaller systems where we did the experiments. So this, in some configuration, this is this completely existing string. This is completely broken one, and they're by tuning this locally tuning, so we kind of bring this up and down in energy, while sort of keeping the other configurations essentially fixed. So you can either have it in the ground state, so then you don't expect anything, or you can bring it into resonance with a process that it could reach through some higher order interactions by sort of creating pairs and moving them and removing them, and eventually going to this fully broken string case. This is, as a test case, we first don't do a quench. Okay, so we prepare the ground state again by this adiabatic state preparation. We prepare this perfect string, and then we just hold it. And we monitor here. So we monitor all these configurations. I'm showing you the 3 here, which is the initial string. So it's now here. This product state string in this subregion is, prepared with like 50% or so. So it's dominated by that. And there's a little bit of noise floor or dressing or whatever it is that also includes sort of the fully charged case. This is this orange one, sorry, the green one, or the fully broken one down here. So you see that's roughly sort of, in some sense, the coherence of the experiment. If you just hold it, it decays a little bit and it drifts, and this is sort of the floor of what we can tell in this real-time resolution. So now you tune this locally tuning such that these two come into resonance. And then what you see is string breaking in real time. So there is some sort of, more or less coherent oscillation that is damped that shows you that this initial string is actually converted into something else, and then it oscillates a little bit. And what I find quite interesting is that you immediately go to this sort of broken case, and there's just a little bit of sort of increase of, for instance, this charge configuration, which naively you would expect you need to go through. Okay, so it's in some sense a onset of something that's non-perturbative that sort of makes this higher order transition, at least, the level of this 10% that we can tell. So it's really sort of, almost in phase. You go from a string to a broken string and sort of back, and then this whole thing decays. So I guess it's sort of one of the main findings, which I think pretty cool. So here, by the way, there is no theory simulation that lies on top of this. Here.
If you could estimate this, like you could do some perturbation theory.
Yeah.
The timescales roughly.
So perturbation theory doesn't do it.
Okay. I see what you were saying.
Yeah.
Victor. The question.
So you mentioned that the string exists and then breaks, and then there's a little oscillation. Do you expect that of the system that you want to simulate, or does the string tend to stay broken in that ideal context?
So it depends what you call ideal. So this is a U1 quantum Ling model, and this is the physics we expect in that particular model. So that's the phenomenology we were after. So in that sense, we're happy with that. If you mean by ideal, let's say QED or QCD, then no, this is very far from what it actually does, but it's sort of phenomenologically very similar.
Okay, can you imagine tweaking your model to achieve behavior more like that?
I'll get to that in the very end if I may. So basically, we want to add more terms and some extra leadership freedom. I think it's possible, but it's not so easy. So you can also look at this in real space. So by the way, should I stop at sharp 12 or like it's time for?
Well, we have you till 3.
Yeah, no, it's just that maybe somebody wanted me to finish at 45 and ask 50 minutes of questions. No, okay, then I just continue.
Yeah, I don't know. Yeah, maybe like try and get to your conclusions.
Yeah.
So that
Almost there.
people can like appreciate it.
Yeah. Okay, so you can also look at this in real space. So once again, this is a little bit harder to see, which is why we focused on this a little bit more quantitative probabilities. But you can see that sort of at initial time, the string is, it's not a perfect string, but it's sort of visibly a string. And then at later time, sort of here, you do see some of this sort of loosening, and also it depends a little bit on color bar, of course. But you do see that there's some, color in here that indicates this breaking and the dynamical charge is being produced. You can also play this game a little bit further. You can break it further by sort of shifting this further up in energy such that it becomes resonance also with this fully charged state that we didn't see before. And then you see that this is two-stage sort of process. So there's more or less a direct oscillation between the string that rapidly decays into this configuration, and then by sort of the second order process, and then directly this couples to the broken string, which then also follows. So this gets more and more richer in the dynamics. And this sort of resonance we also analyzed a little bit more carefully, now comparing also to theory. Sorry, this is the experiment. If you repeat this, what I just said, and you record at a fixed time the probabilities, you see that there's this resonance that roughly around where we expected. You see a dominant production of these broken strings, and then at a later time, you dominantly produce these fully charged states. And this is how it looks like in theory. Okay, so we clearly have some sort of broadening going on that is not captured by the pure sort of, well, the pure state MPS type simulation, but the structure is sort of the same. You have this type of resonance that is located at some point. This location you can actually very simply understand just from sort of the crossing of these energies that I was alluding to. So you can calculate the classical configurations of these product states, the energies, and when the string sort of crosses these broken strings, that's roughly when this resonance happens. And that is, well, this is corrected a little bit for the second process. Also sort of the shape of the resonance, which is a little bit, it's not really a resonance, it's an asymmetric thing, is also partially reproduced. And then we also did this for larger distances. So this is sort of going towards more and more complicated situations. For this particular procedure, what also happens is that the process is just further suppressed. Like you need, if you have larger distances, you need more and more sort of higher order processes. So you expect also that the overall probability goes down. And this is also what we see here, but still this resonance argument still works and it's sort of qualitatively compatible. Okay, so with that, I'm coming to the end. I hope I could give you a flavor of this analog type quantum simulation that you can do with existing hardware. So we, on one hand, studied this sort of ground state physics, so equilibrium, reproducing these features of the broken and unbroken strings. And then we started sort of playing a little bit with this real-time dynamics where you can really sort of resonantly or non-resonantly see string breaking. And now coming back to your question, what is missing to make it behave more like QED are plaquette interactions. So the gauge fields here only do dynamics because they are coupled to charges. So to actually sort of get the physics of the gauge fields themselves, we need to make them propagate. So we would need to add another term. And this doesn't come for free here. So there are some ideas how to do sort of digital approaches on where you could engineer a plaquette term. So this is also coming back to your question. I think would be kind of cool to combine a hybrid, sort of more programmable device where you maybe use that you can freeze the whole state in a configuration that is in digital mode. So then you do your analog evolution for some time, you freeze it, and then you do one digital trotter step, for instance, of a plaquette, and there could be something would be interesting to explore in principle. Personally, I'm kind of convinced that eventually we will need to go to quantum computers. So this is, I think, pretty cool physics that we can still do for some time, but eventually, if you actually want to do QCD, probably need a fault-tolerant computer and then other methods as well. So I'd be very happy to chat about that. We have some ideas about how to do this. Also using, going towards more realistic models, this question about truncating large Hilbert spaces and maybe using qubit quantum computers to do that. And with that, I'm coming to the end. Finally, an advertisement. So I'm actually looking for building my own group soon. So if you know somebody who's interested in working on digital simulations of nonlinear and lattice gauge theories, I will be looking for PhD and postdoc positions in the near future. And with that, thanks for your attention.
You did mention fermions on the.
Yeah.
There's no fermions here.
That's right.
That's also important? Or?
Yes. Right. So I should have said that, yeah. So the matter degrees of freedom in here are in some sense hardcore bosons. Right. So that's another way in which this is not sort of real QED. And for this physics, it's not really important yet. But eventually, it is absolutely crucial that fermionic matter is fermionic because it's sort of the different types of bound states you can build out of these things that are sort of attached by strings and really matter that it's fermions. So in this particular setup, we don't have fermions, but ultimately we want them. And that's a super important open question on how to, well, either do them with fermionic hardware or maybe with some encoding.
But so you're saying Q, so it's actually better to go to QDIS and then figure out fermions rather than.
I'm not settled on what is the best. So I think
This is beautiful physics. So.
Yeah. I think in the long run it's open what's sort of the best encoding strategy. Or
The other question?
So you did see new physics that you didn't know about before? Stuff.
One thing that-
well, we could have known them if we studied this model before, right? So, like we saw the physics that we expected in the sense there exist these confined flux strings and they can break, and we didn't know precisely how they will look like, but mainly because nobody has studied this particular lattice gauge theory. So to see something that we cannot simulate, we would need to push the system larger. For instance, how these strings thermalize in the end. That's something we cannot predict.
And you're saying you can't do this without fault tolerance? I mean, it's a phase of matter.
No, I think in this model you can. I guess if you push these experiments further, you will be able to study exactly a phase of matter and its properties in a way that sort of it goes beyond what we can do with classical computers, and for which fault-tolerant computers are probably not necessary. What I meant is more that if you want to simulate QCD, let's say, okay, which is not this model, then it gets much more complicated than this model, and I am not convinced that it's easy to find it or even possible to find an analog implementation of that. So I think for that you will eventually need digital computers. That's my opinion.
Nice. So can you, maybe in the same sphere, can you talk about the experiment? What did the experiment add to this, or what did we learn about the experiment?
So I think, well, I'm not the experimentalist, obviously, but I think there were some sort of actual noises in the device that they realized they had to fix that was not clear, for instance, in the adiabatic state preparation, or so of some technical aspects where it actually took a while to get sort of this nicer data. And I'm not entirely certain exactly, what they fixed. But there were some aspects where they sort of realized that things are not going precisely the way they wanted. But I'm not.
And you said it's very hard to do numerics of these adiabatic protocols.
No, I think that's actually okay. We didn't do it.
So you didn't.
It's technically straightforward, but it's sort of relatively expensive in the sense that you need to do a bunch of relatively large scale simulations, and it was not necessary to sort of reproduce what we had. At that level. Yeah.
Well, if you were able to do like a 3+1, like a quantum computation of like a 3+1 dimensional model for QCD, like what would you want to explore in the real-time dynamics? Like where would you go to like find new physics, or like what would be interesting?
So I think, so for instance, I mean, what people are doing in heavy ion collisions, they have certain models on how this thing thermalizes. So a big question that certain communities always after is how does the quark-gluon plasma actually thermalize? So they have a whole set of approximations where you do some sort of a lattice calculation and then you cross over to hydro. But to my understanding, one thing that is sort of not completely settled is why does hydrodynamics work as a description early on? Okay, and that is not unlikely. I think that this process needs to understand why that is happening. We need to understand the quantum dynamics in more detail. So I think that's the direction I would sort of personally pursue. Sort of do a real-time evolution, try to see if you can sort of see the emergence of hydrodynamics quickly, and try to understand that.
Do you have a preferred QDIT platform?
Well, I like ions.
There have been promising developments in
So there is a group in Innsbruck by Martin Ringbauer who actually has a trapped ion qubit quantum computer. That's one of the reasons I like ions, because they actually exist as qubit quantum computers.
How large is the D there?
Yeah, so he has a setup with where he can basically use these 8 internal levels. So it's sort of 3 qubits in one if you wish. He's also building an experiment with more internal states. That would be on the order of 20, I think. So that's sort of within reach. Apart from ions, I obviously like neutral atoms. And I think there is an opportunity to sort of also do qubits with neutral atoms. If you go, for instance, to alkaline Earth-like elements, you have large ground state manifolds where you could encode qubits. This is also being pursued by some people. Also in this reference that I mentioned, we made a proposal how to combine this with the idea of fermions. So in contrast to trapped ions with the neutral atoms, they actually come as fermionic atoms. So these multi-level sort of atoms, fermionic atoms, something like strontium-87, for instance, could play a dual role where if you either sort of keep them fixed in place, you can use the large internal states as a qubit, and then you could also maybe just pick two of them as your spinful fermion and potentially spatially delocalize that, so also harness its fermionic nature. So in some sense, there's a possibility to think about hardwares that sort of naturally represent both large internal Hilbert spaces and qubits. But I would say it's pretty open how to sort of exactly do it. Like the experimental ingredients are sort of individually sort of capable, like existing, but you need to combine them. Also, the question of how to actually build a computer with that, error correction, fault tolerance on top of that, I think is basically open.
Maybe a follow-up to her question. So
Mhm.
since QCD simulation may be far away, so I wonder in the near future, like in 5 or 10 years, what would you like to study?
So I think I will probably stay in 2D just for simplicity. So sort of variants of QCD in 2D. I think that would be cool. Of course, the physics is a little bit different, but some of the aspects are relatable. So I think, well, for instance, doing non-abelian engaged theories coupled to fermions in 2 spatial dimensions, I think that already has quite rich physics, for instance, about the thermalization story. Trying to see hydrodynamics emerging there. I think that would be a cool application.